Today we're doing a question on calculating head loss in a turbulent pipe flow system. So you're tasked with designing a water supply system. It involves transporting water through a horizontal pipe. So we've got a horizontal pipe. Okay. And we have water traveling through. The pipe is made of commercial steel. Okay, which has a roughness height of 0.045 millimeters, which we're going to convert straight away to meters. We know that in this case, we're going to have turbulent flow conditions, but if a question were to come up, it's something you'd want to check. Okay, so we also have the water is at T equals 20 degrees C. That's important to note because of things like changes in density, and that's going to change your viscosity, which is going to affect your flow. So we're talking about normal water with a density of around 1,000 kilograms per meter cubed. The inner diameter of the pipe is going to be 0.2 meters. And we have a 100-meter length of pipe. Okay. We're given the flow rate to be 0.05 meters cubed per second. Okay, so the steps we're going to take to solve this problem. I always emphasize working backwards. So the first thing we want to do is to highlight what we're looking for in the question. So the thing that we need to find is head loss due to friction, and that'll be the final thing that we end up calculating. To get head loss due to friction, we're going to use the Darcy-Weisbach equation. This will probably be given, but it's also one that if you use it often enough, you'll end up learning. Over d v squared over 2g. So we have F is our friction factor, which we're going to talk about soon. L is the length of pipe. We tend to stick to everything in SI units, so that would be in meters. D is the diameter of pipe, again in meters. V is the velocity of our flow. This is the longitudinal velocity along the length of the pipe, and that is in meters per second. And g is our acceleration due to gravity, taken as 9.81 meters per second squared. Okay, so to be able to solve this, as I said, we need to work backwards and identify what we have. Now we're given in the question length and diameter. We know g, so we need to identify what are the friction factor and the velocity. Velocity is fairly simple. We just use our value for discharge. Discharge is going to be our velocity times the cross-sectional area of the pipe. So here's our pipe. And it is this face, it's that cross-sectional area that the flow is moving through. So we can rearrange this to give velocity is equal to Q over A, where the area is equal to pi r squared. or pi d squared over 4. So that is the r is the radius and d is the diameter, as mentioned before, and both of those in meters. So that will give us area of pi 0.2, is it? Yeah, 0.2 squared over 4. We just calculate that, and we get we leave it in terms of pi over 100. That is roughly 0.0314 meters. So our velocity is therefore 0.05 over pi by 100. 5 divided by that gives us 1.59154941 meters per second. So if you're in an exam, I would write out the full number and then round it up, just to emphasize that you know the original value and that you are rounding. So that's our velocity. So now we've got that. We just need that friction factor. Now, the question, it does ask us to find the friction factor, but you won't always be told the order of things to do. So like I said, it tends to work well to think about what's the last thing I need to find and work my way backwards. So to get the friction factor, we need to know if we're in turbulent or we need to know if we're in turbulent or laminar flow, so that we know how to use our Moody diagram, which I'll show you in a second. To calculate Reynolds number, we're going to use our equation, density, velocity times characteristic length over the dynamic viscosity, where the dynamic viscosity is just, the kinematic viscosity is equal to the dynamic viscosity over the density, and therefore 1 over the kinematic is equal to density over dynamic, giving us velocity diameter over kinematic viscosity. So that gives 1.6, which we calculated earlier, 0.2, which is the diameter, and the kinematic viscosity of water at 20 degrees C is given as 1.004 times 10 to the minus 6. 1.004 times 10 to the minus 6. That will give us a value of 1.6.2 divided by 1.004 times 10 to the minus 6. 3.18725. So roughly 3.2 times 10 to the 5. So that's definitely turbulent, as it is over 2000 considerably. So we go to our Moody diagram. First thing we need is that Reynolds number. So we go to 3.2 times 10 to the 5. So this is a logarithmic scale. So this represents 10 to the 5, 1 times 10 to the 5, 2 times 10 to the 5, 3 times 10 to the 5, and so on up to 10 to the 6. Once we reach 10 to the 6, we now change our scale. This is 1 times 10 to the 6, 2 times 10 to the 6, 3 times 10 to the 6, and so on. This is 1 times 10 to the 7, 2 times 10 to the 7, 3 times 10 to the 7, and so the pattern is repeated. So for 3.2 times 10 to the 5, we're looking at 1. That's 1, that's 2, 3, a little bit past it. So if we say about there, so we just mark our line straight up, and that's where our 3.2 times 10 to the 5 Reynolds number is going to be. Now to read the friction factor, we're going to need to identify our pipe relative roughness so that we can determine which of these lines we need to use to read off. So our relative roughness is given as the pipe roughness height divided by the diameter of the pipe. Now, the pipe roughness height was given as 0.45 times 10 to the minus 3. Remember to do this in meters. 0.045 times 10 to the minus 3, and the diameter was 0.2, giving us a relative pipe roughness, 0.045, 3 divided by 0.2, of 2.25 times 10 to the minus 4 meters. So again, we find where 2.25 times 10 to the minus 4 might be on our right-hand axis. So we have 2 times 10 to the minus 4, 5 times 10 to the minus 4. So it's going to be somewhere between these two. As we're going up, we're going bigger. So it's just probably a little bit higher. So maybe around about here. So if we trace this line slightly above it, following the pattern, it's going to come in a bit tighter, and then about here, I would say. We're going to read off to the side. It's not vital that you get this bang on. What's more important is that you are demonstrating how you've done it. Now, in this example, they've approximated the friction factor to be 0.02. Our value is going to be a bit less than that, at about 0.0175 by my estimation. So we go back to our calculations, and we have now got friction factor. So maintaining what our points were, we want to find the Reynolds number, which is what we have done. Using that, we've got our friction factor from the Moody diagram, and now we can calculate head loss using the Darcy-Weisbach equation. So HF, our head loss, is equal to the friction factor times the length over the diameter times the velocity squared over 2g. Friction factor we said was 0.0175. The length 100 meters, the diameter 0.2, the velocity 1.6 squared, and 2 times 9.81 for the acceleration due to gravity. So putting all those values together, 1.6 squared divided by 2 times 9.81 times 100 divided by 0.2 times 0.75 gives us 1.14 meters of head loss from across the length of the pipe. Bear in mind, this obviously doesn't account for any minor losses. There are no bends, there are no expansions, etc. The only loss we really have is due to the length and friction of the pipe.